Hello and welcome. So in this presentation, we are going to talk about a different way of approaching line integrals. So before we do talk about that approach, let's just quickly review the fundamental theorem of line integrals. And that is if you have the line integral of the gradient of a function, that can be solved by evaluating the function at the endpoints along the curve. However, and also in this, if you have a vector field that is the gradient of a function, we can then also apply this. So now, applying this, consider two different situations, one of which we can apply the fundamental theorem and one of which we cannot. It is suggested that at this point, you pause the recording and attempt each of these. So with that opportunity, let's continue. So for this first one, the one on the left, we have the integral along a path of f dot dr, where f is equal to y cosine x plus secant squared x, comma, sine x plus 3y squared. So we note that f is the gradient of a function y sine x plus tangent x plus y cubed. Because, for example, if we take the gradient of that, derivative of sine x with the derivative of y times sine x with respect to x is y cosine x. Derivative of tangent x with respect to x is secant squared x. And the derivative of y cubed with respect to x is 0. That results in the I hat component of this. Taking the derivative of this function with respect to y, derivative of y sine x with respect to y gives sine x. Derivative of tangent x with respect to y gives 0, and the derivative of y cubed with respect to y gives 3y squared, and so that gives the j hat component. So this is a conservative vector field, meaning the vector field is the gradient of a function, and we've identified the function. For more information on how to do this, check the recording of the class on the fundamental theorem of line integrals for a procedure. Now that we have this vector field as the gradient of a function, we can then evaluate this at the endpoints of the curve as the solution to our line integral. We note that the curve goes from 0 to pi over 4. So at the endpoint at pi over 4, we have the point pi over 4 comma pi over 4 cubed, and we can insert that directly in for y and x. So instead of y sine x, we have pi over 4 cubed sine pi over 4. Instead of tangent x, we have tangent of pi over 4, and instead of y cubed, we have pi over 4 cubed again, which is pi over 4 to the 9th. Plugging in the other endpoint of the curve, which is 0, we get the point 0 comma 0. We note that sine of 0 is 0, tangent of 0 is 0, and y cubed, meaning 0 cubed, is also 0, hence the minus 0 at the end. From there, we could just use a scientific calculator, and so for our purposes, it's complete. Now, let's look at the second one. That is the one on the right. If you may recall, in order for a vector field to be the gradient of some function, we should take partial derivatives of the other with respect to the other variable for its position and see if they are equal. Meaning, we can take a partial derivative of xy cubed plus 5y with respect to y and compare it to the partial derivative of 3 over 2 x squared y squared plus 7xy with respect to x. So taking the partial derivative of xy cubed plus 5y with respect to y gives 3xy squared plus 5. If we take the derivative of 3 over 2 x squared y squared plus 7xy with respect to x, we get 3xy squared, which does match, but then we also get plus 7y, which does not match with the plus 5 we had. So in this case, we have unequal partial derivatives with respect to other variable. And so the key thing here is this vector field is not the gradient of a function, and so we can't apply the fundamental theorem. And in some cases, line integrals are straightforward to solve. In other cases, they're flat out annoying. And so an example of such a case would be this case of a line integral where we are talking about a region that is bounded by 3 separate segments. So similar to a homework problem, we have the line integral of 7x squared y dx plus 5xy dy bounded by 0, 0, 0, 4, and 4, 0. By the way, this vector field 7x squared y comma 5xy is not one in which there is a gradient. If we consider the cross partial derivatives, derivative of the first one with respect to y gives 7x squared, derivative of the second one with respect to x gives 5y, which are clearly not equal. So that then, without an additional theorem, that gives us the only option being to parameterize the path around the perimeter. So using the orientation, using that it is going counterclockwise, the first segment, which is a diagonal line between 4, 0 and 0, 4, becomes 4 minus t comma t. To go over the reason for that, note that we have y equals 4 minus x. However, we can only go in the other direction, and so that's the reason for the reversal on that with respect to where the parameter is. And that's from 0 to 0 is less than or equal to t is less than or equal to 4, representing that we start out at the point 4, 0 when t is 0, and we end at the point 0, 4 when t is 4. That is the first segment. That would be the diagonal line between 4, 0 and 0, 4. The next segment is the vertical line between 0, 4 and 0, 0. So for there, we start out with y is 4 and x is 0, and then y decreases, which is the reason that y is 4 minus s, where 0 is less than or equal to s is less than or equal to 4. The final line segment goes from the origin to the point 4, 0, and that's represented by u comma 0, for u is between 0 and 4. Now we have an additional process, because what we have to do is for each of these line segments, we need to plug in our parameterizations for x and y. We also need to find dx dt and dy dt and multiply those parameterizations by that derivative in the place of dx and dy. Doing so gives this integral, which is done in 3 parts because we have 3 different line segments. It is worth noting this is not as bad as it might seem, since 2 out of the 3 integrals being added are 0. Because conveniently enough, this function has x and y being multiplied on both parts, and also note that on 2 out of the 3 line segments, either x is 0 or y is 0, which makes both parts of this integral end up being 0. Still, it's a lot of writing, it's a lot of determining things, and from this result, we get negative 96. Now we are going to do an example that explores another method. It is suggested that you try this on your own and then listen to the recording after that. Getting started with this, we are going to consider the double integral from 0 to 4 and 0 to 4 minus x of 5y minus 7x squared dy dx. We integrate first with respect to y. which gives 5 over 2 y squared minus 7x squared y evaluated from y equals 0 to y equals 4 minus x. Plugging in the bounds gives the integral from 0 to 4 of 5 over 2 times 4 minus x squared minus 7x squared times 4 minus x dx. Using a computer program, this results in negative 96. Now, consider how this integral, that is the inside of this integral, relates to the previous problem. If we look, the j-hat component of the previous problem was 5xy. The derivative of that with respect to x is 5y. The I-hat component of the previous problem was 7x squared y. Derivative of that with respect to y is 7x squared. And so not only do we have the same answer to the integral, we have a relation in terms of partial derivatives of the previous problem. And so that gives us a base to start from for a new theorem to calculate these differently. Moreover, if we look at the bounds of the integral are 0 to 4 minus x on the inside, which represents the x-axis to the diagonal line between 0, 4 and 4, 0. And the limits on x are 0 to 4. This is the exact same region that was enclosed by the three lines. And both the inside of this integral, the region, and the answer are not a coincidence. Instead, they are leading us towards a different theorem that allows us to convert some line integrals into double integrals. The result in the previous slide is an example of Green's theorem. Green's theorem says that if we have an enclosed region with particular properties, which, by the way, most regions you will deal with have these properties, and the ones that don't will stand out because they're not normal regions. But if we have an enclosed region with some general properties, we have that the line integral around that region is equal to the double integral with respect to that region of the derivative of the y component of the vector field with respect to x minus the derivative of the x component of the vector field with respect to y. So generally, we have cross partial derivatives that are being subtracted. And this can allow us to take a line integral that is complicated, confusing, or time-consuming and make it into a simpler double integral. For example of where Green's theorem can be applied, consider the line integral around the curve, which is a triangle with vertices 0, 2, 5, 2, and 5, 7. It's oriented counterclockwise, although that's the standard way, which results in a positive double integral, so we're going to leave it at that. So to compute this using Green's theorem, we first of all take the mixed partial derivatives. So in this case, the derivative of the y component with respect to x is 3, since the derivative of 3x with respect to x is just 3, and the derivative of y with respect to x is 0. And the derivative of the x component with respect to y is 0, since there aren't any y's in sine of x squared, and so the derivative with respect to y of sine of x squared is just 0. So next, we need to determine the bounds of the region. So for the bounds of the region, we note that 2 out of the 3 points have y equals 2, so we use that as our lower bound. For our upper bound, we have the line segment connecting 0, 2, and 5, 7. So, first of all, the slope of this, which is rise over run, and it's a line segment, is 7 minus 2 over 5 minus 0, which gives 5 over 5, which is 1. It also has a y-intercept of 0, 2, so using slope-intercept form of a line, we have y equals 1x plus 2. So the bounds for y are from 2 to x plus 2. Then the bounds for x are 0 to 5. So now, using the difference between the crossed partial derivatives, where we have q sub x minus p sub y is 3 minus 0, can take an antiderivative with respect to y and plug in. Antiderivative with respect to y of 3 is 3y. Plugging in the limits gives 3 parentheses x plus 2 minus 3 times 2, which is 6. And we end up with the integral from 0 to 5 of 3 times x plus 2 minus 6 dx, which, when entered into a computer program, results in 37.5, and that's all we have to do. A different application of Green's theorem is transition from a double integral into a line integral, or in other words, this is generally done to find the area of an oddly defined region. So consider the area defined by the vector value function r of t is equal to sine t cosine t, comma, sine t on 0 to pi. Looking at this forms a really weird region, and any attempt to do this by a single integral is likely going to be very difficult because we are looking at multiple oddly shaped boundaries, and so we want a way to go from this vector into a double integral that is reasonably simple. We note that there's a relation between a double integral and a line integral that we saw in Green's theorem. Also note that the double integral of 1 times dA is the area. Now, what that means is we want the derivative of q with respect to x minus p with respect to y to be equal to 1. The simplest way to do this is to set derivative of q with respect to x minus p with respect to y equals 1, and that means q is x and p is 0, because if we have that, then the inside of the double integral is 1. So we can insert this into the line integral, and also note that for the bounds of our line integral, x is equal to sine t cosine t, and y is equal to sine t, meaning that that means that we are going to have the line integral given that q is x. So the first part of the line integral is just going to be 0, because p is 0, so dx dt doesn't even matter. So that means we are just adding what we have for x, which is sine t cosine t, and then the derivative of y with respect to t, since it is q times dy, which translates to what we have for q from the vector times dy dt. If we look at the function r of t, the derivative of the y component, which is sine of t, with respect to t is cosine t. So x replaced becomes sine t times cosine t, and then dy dt is sine t. Given that the bounds are 0 to pi, this gives us the integral from 0 to pi of sine t cosine t times cosine t dt. Now, this is the same as the integral of cosine squared t times sine t evaluated from 0 to pi. By the way, you could also do this using a computer integration program. Using a u substitution, u being cosine, then du is negative sine, becomes the integral of negative u squared du, which is negative 1/3 u cubed, or in other words, 1/3 cosine cubed t, evaluated from t equals 0 to t equals pi, and we get 2/3. So the integral of this region is 2/3, and it can be found by converting the double integral of 1 dA into a line integral of p dx plus q dy. and then solving. The concept we're going to go over today is a concept that also involves mixed partial derivatives in vector form, and this is the idea of curl. So the curl of a function PQR, where it's a vector field, P is the x component of the vector field, Q is the y component of the vector field, and R is the z component, where each of these are functions of x, y, and z. The curl of this vector field is derivative of r with respect to y minus the derivative of q with respect to z in the I hat direction, plus derivative of p with respect to z minus r with respect to x, the j hat component, plus derivative of q with respect to x minus p with respect to y in the k hat component. We can also write this using the symbol of an upside down triangle. It can either be said as del or as nabla. So we can write this as, so by the way, del is partial with respect to x in the I hat, partial with respect to y in the j hat, partial with respect to z in the k hat. We can write the curl as del cross product with f. And this is a way of remembering it. You could just remember this formula. However, for me personally, I prefer this way. But again, it's up to you. So now we're going to calculate the curl of the function x cubed y in the I hat plus x squared y cubed z in the j hat plus 3xz minus 5y squared z in the k hat direction. So first of all, note that the curl of the function is del cross f. We can use a matrix to represent the cross product where we have I hat, j hat, and k hat on the top line. Then we have what del is. So del is ddx in the I hat, ddy in the j hat, and ddz in the k hat. And then the vector field goes on the bottom line. So x cubed y plus x cubed y, x squared y cubed z, and 3xz minus 5y squared z. So for the cross product, we take I hat, we cross off the first column and the first row. Now the partial derivative of y with respect of 3xz minus 5y squared z is 10yz minus x squared y cubed, because derivative with respect to z of itself is just 1. And then we subtract, we're going to cross out the first row and the second column. So that gives j hat times, we got ddx of 3xz minus 5y squared z. So that becomes 3z, since the derivative of 3xz is just 3z. And then there's nothing else for this because the derivative with respect to x of 5y squared z is 0. And then we subtract the derivative with respect to z of x cubed y, which is 0. Lastly, we cross out the first row and the third column, and we have ddx of x squared y cubed z, which is 2x y cubed z, since the derivative of x squared is 2x, and then y cubed and z tag along. And then we have ddy of x cubed y, which is just x cubed, since the derivative of y is itself. This is the answer to our curl. So the curl of a function is a vector field, and simplifying it usually is not necessary. Lastly, let's consider the curl of just a two-dimensional vector field. So a two-dimensional vector field has an advantage, and that is we write in 0 for the z component. Also note that there aren't any z's in either one of the components. So because of that, ddz of either one of these is 0. And what you'll notice is that crossing out the first column and the first row, we have ddy of 0, and then ddz of something not involving z, which gives 0. And then crossing out the first row in the second column, we have d dx of 0, which is 0, minus d dz of something not involving z, so that's also 0. So the only component that is non-zero is the k-hat component. And crossing out the third column in the first row, we have d dx of xy squared plus 5x squared y, which is y squared plus 10xy. Then we subtract, we got d dy of x cubed y squared, which is 2x cubed y, since the derivative of y squared with respect to y is 2y. That's all for today. I realize that's a lot. I will be lenient with you on this. I'll see you all on Wednesday.